Hello, my name is Punyapa Titichoatrattana and I'm come from 1103 and today I'm gonna talk about the electric current, which is the chapter 22 of the physics class. So let's get started with the electric current of the chapter 22. We have to know first what is the electric current. The electric current is actually means the flow of electric charge. Producing electric current is when two conductors touch and charge flow from the sphere at the high potential to the one at the lower potential until there's no potential difference between those two conductors. And conventional current is mean the direction in which a positive test charge moves, and usually it is negative charge or the electron that flows. And the flows of the electron and the direction of the conventional current is actually opposite. Here's the example of the object B, object C, and object A that is touches each other. As we can see, the positive charge is moving downward to the object A so that until the object A, B, and C is equally having equally charges until there's no potential difference. Okay, so we have to know what is battery. The battery is the device store chemical energy and make it available in an electrical form. The electrical circuit is mean any closed loop or conducting part that allows the electric charge to flow. The circuit includes a charge pump which increases the potential energy of the charge flowing from A to B, the device that reduces the potential energy of the charge flowing from B to A. And here's the formula for the potential energy loss is going to equals to Q times delta V. And the potential energy loss is usually converted into the other form of the energy. The electric circuit, and as we know from the latest chapter, the charge is conserved quantity, which just means that it cannot be created or destroyed. The total amount of charge is that the number of the negative electrons and positive ions in the circuit does not change, and the energy is also the quantity that also conserved. As we know from the previous slides, the change in energy or the delta E is actually also equals to Q times delta V. Because charge is conserved, the net change in potential energy of the charge is going to be 0. Okay, so let's move on to the rate of charge, flows, and energy transfer. The rate of flow of the electric charge, or the Q over T, is called the electric current, which can be represented by I. So there's a new formula. I is equal to Q over T. And the SI unit for this is ampere, or a flow of the 1 coulomb per second. The energy carried by the electric current depends on the charge transfer, or the Q, and the potential difference across its move, or delta V. And here's the concluding formula. And in this meaning, power in this meaning is mean the power delivered to an electrical device. So let's having a problem solving. Here's the problem. A 120 volt motor operates at 13 ampere. Determine the power and the energy used in 1 hour of the operation. So what we know is the delta V is equal to 120 V and T is equal to 13A, and we know that our T is equal to 1 hour or 3,600 seconds. As we know, but we don't know the P and E. As we know from the formula we have just talked about, the P is equal to I times V is going to be the 120 V times by 13A, and it's going to equals to 1.6 kilowatt, and the energy is going to be P times by T, and the result is going to be the 1.6 kilojoules per second times 3,600 seconds, and it's going to equals to 5.8 times 10 to the power of 4. Let's move on to the diagramming circuit. It can be described in many ways. For example, for the first one, we can use a drawing like this, or we can use these schematic diagrams like this. It's actually very well known, and here's some very common example of these schematic diagrams. Let's move on to the resistance and Ohm's law. The resistance is actually means the property that determining how much current will flow, and it measured by placing a potential difference across the conductor and dividing the voltage by the current. And so here's the formula. It is R is equal to V delta V over I. And we can using the Ohm's law applying to this. Like I total is equal to E total over by R total. And the resistance is actually measured in ohms, which can also use the Greek letter to represent the ohms. And here's this one, the omega 1. 1 omega permitting 1 to flow when a potential difference of the V is applied across the resistance. It can be used in the schematic as this one. And device having a constant resistance is dependent of the potential. If different is actually obeying the Ohm's law. And there's two things about it. The most metallic conductors obey Ohm's law at least over a limited range of the voltage, and the transistor and the diodes are important electronic components that do not obey Ohm's law. Let's move on to the parallel and series connection. The parallel connection means when a voltmeter is connected across another component. It is because the circuit component and the voltmeter are parallel to each other, and the potential difference across the voltmeter is equal to the potential difference across the circuit elements. Quick reminder for this diagram, the I is equal to current and V is equal to voltmeter. And the next one would be the series connection. The ammeter is being the device used to measure a current through the circuit component, and the series connection is mean the connection with only one current part. And the current are equals for all the entire part, and here's the formula. It is ER1 is actually equal to ER1 times R1. ER2 is equal to 1R2 times R2, and continue on. So to let you having a pictures about it, let's move on to the question about the series circuit. Here is the diagram, and on the first resistance, the first resistance having a resistance of 3 kilo omega. The second one was 10k omega, and the third one is 5k omega, and the voltage in total is 9. As from the formula that we talk about, the energy of the resistance 1 is going to equals to 500 mu A times 3 kilos omega, and it's actually equal to 1.5 volt. And the second resistance was 500 mu A times 3 kilo omega is equal to 5 voltage, and the third one was 500 mu A times 5k omega and is equal to 2.5 voltage. Okay, I forget to mention that there also the 500 mu amp as the current flows of this whole system. And after we added up those 3 voltage, we also get 9 voltage, which means that this one is the series circuit, and it is correct. Let's having another example of the single resistance circuit. Here is it, and there's 9 voltage, just like the latest question, but there's only one resistance, which is equal to 3000 omega. And because of the formula from the current is that current is equal to energy over the resistance, we can write it as 9 volt over by the 3 kilo omega, and we're gonna get the result of 3 mA as the current of this whole system. Okay, so So because of I haven't mentioned about the parallel circuit formula yet, I will show you what is it. And for the parallel circuit, the R total is going to be 1 over R1 plus 1 over R2 plus 1 over R3 and continue on. It may be a little bit confused, so let's check it on the example in this one. So this system, there's an battery which contain 120 voltage and the resistance 1 and resistance 2. And after we doing the calculation, we would get the current for the first part on the first part on this one, on the R1. We gonna get the currents of 6 amp. Write it down on the diagram. And for the first on the second part, we can get the 2 amps, and on the third part we get the 8 amps. And this is how the current flow would be. So let's move on to the section 2 of this chapter, which is going to be the electrical energy and resistance and power. The energy supplies to the circuit can be used in many different ways. For example, the motor can turn the electric energy to be the mechanical, and the lamp can turn the electric to be the radiant energy. All the device converts some electrical energy into thermal, and the current moving through the resistor caused it to heat up because flowing electron bump into the atom in the resistor, and this collision is also increase the atom's kinetic energy and thus the temperature of the resistance. So this is the visuals of the household applicants that act like a resistor when they're in the circuit. And when the charge or the coil is moved through a resistor, its potential difference is reduced by amount or the V, and the energy change is represented by the Q delta V. So we can write the formula as P, or power, is equal to I current times delta V is equal to I squared times R and equal to delta V squared over R. Superconductor is the material with a zero resistance. It has restrictions and no potential difference or delta V across them, and it also can conduct the electricity without loss of energy because of its power that is dissipated. Let's see the practice problem. The question states that a water heater operates at 240 volt, and the resistance of its heating element is 12 ohm, and it asks how much current does it demand and how much thermal energy will it produce in 30 minutes. So what we know is that we know delta V, which is equals to 240 V, and we know the resistance, which is the 12 ohm, and we know the T, which is 1800 s second. And what we don't know is that we don't know I and we don't know E, so we will use the formula for finding I of delta V over R, which is going to be 240 V over 12 ohms, and it's going to equals to 2 times 10 to the power of 1 amp. And for the E, we're going to use the formulas of PT, which is going to be I squared times RT. So it's going to give the answers of 8.6 mJ. Let's move on for the providing electrical energy. The power is the rate at which the energy is delivered. So when the consumer pay for the bill, they pay for the electricity. And they pay for the electric energy. And what we have to know, another thing, is that the kilowatt is the 1000 watts that is delivered continuously for 3600 seconds. So its value can be say as the 3.6 times 10 to the power of 6 joules. And that is all for the whole chapter. Thank you for listening.